3, or is this way back from like biology 200 A and B, the high and low concentration of solutes and the way that they move? Okay, so it's back there a little bit. All right. Okay, so left to its own devices, so this would be, I'm just going to make these numbers up, but let's say this is a 10 molar concentration of potassium, all right, and this is a 1 molar concentration of potassium, meaning that the solution over here has 10 times the potassium than the solution over here. And just to make my drawing accurate, I will add 3 more potassium, because that's 10 to 1. Okay, so this is a potassium permeable membrane. Solutes move from an area of high concentration to an area of low concentration. They naturally do that. It's just the way that it works. So if this membrane moves potassium, it allows it to just freely flow from one to the other. What will happen is the net result will be to move potassiums from this side to that side so that both have an equal of potassium. This will happen over time. And it doesn't mean that some of these don't flow back. It means that as it settles out, once it's at equilibrium, these will settle so that the concentration of this will equal the concentration of this. There will be no net movement of back and forth. These things will still move. It's a permeable membrane, and one can hop over there and one can hop over here. But there's no net movement. They will end up at, so there's 10 over here and 1 over there. So it would be the same as, and that's 11 divided by 2, which is like 5.5 potassium ions on each side. Now obviously we don't have that possibility, but that's the idea. You find an equilibrium concentration where you add up all of those and they find themselves equal at the end. This assumes that that membrane is permeable. So in our cells, this is equivalent to the intracellular fluid and this is equivalent to the bloodstream. Does the potassium want to go from here to here or go from here to here? There's way more potassium in our cell than in our bloodstream. So the potassium wants to leave the cell and go into the bloodstream. It wants to try and find an equilibrium. There are 2 things keeping that from happening. One is we do not really have a super permeable membrane to potassium. It can happen, but it doesn't usually. The other one is we spend a bunch of ATP making sure that that doesn't happen. We spend a lot of energy, so here's our ATP, and you'll notice in the book they add the magnesium there. Now, because we're in chapter 34. So, in order to keep this concentration high, which is what we want, we spend ATP to import potassium plus against a concentration gradient. This is what this system wants to do. This is a closed system. It wants to find equilibrium. It wants to put the same number of Ks on both sides of the line. That's just what it wants to do. We don't function that way. This cell needs way more potassium. Oh, sorry, it's the chalk.
Bless you.
Thanks. Than it does inside the cell, than it does outside the cell. So we have to spend energy to make sure we keep bringing that potassium in, because we have to maintain this gradient. That's the job of the sodium-potassium pump. Now at the same time, right, we have way more sodium over here. Sorry. Try to keep my math the same. And again, these are not the real concentrations. I'm just trying to make really simple math, because 10 is 10 times 1, so it's fairly easy to get the visual difference. So there's a ton of sodium outside the cell. There's not very much sodium inside the cell. The sodium wants to do the exact same thing. If this is permeable, it wants to move through this membrane. It wants to move through this membrane to make the same number of sodiums over here as over here. So you'll lose some over here and gain some over here. So it wants to look like this. Right? That's its desired look. The system tends toward finding equilibrium. The cell will not work if we find equilibrium. Everything in our system will not work if we find equilibrium. So we spend energy on the sodium-potassium pump to make sure that we keep more potassiums over here and more sodiums over here. Okay? And then, so... And we're going to go over this in more detail on Wednesday when we start talking about osmosis, because osmosis is the flow of water through a water-permeable membrane, which switches the arrows, but ends up with the same effect, okay? But I want to get this part down first. If we can get this generally okay today, then Wednesday will be a little easier.